I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about diffraction due to single slit. So when we look at the module 4, we have already discussed about Huygens principle, superposition of waves, Young's double slit experiment, expression for fringe width, and also the Newton's rings experiment. You can view the videos related to this for this topic related to Fraunhofer diffraction. Now today we are going to talk about Fraunhofer diffraction from a single slit. So let us see how we are going to go about this topic. First we are going to understand about what is diffraction and then compare it with the interference pattern which we have already understood. So we are going to see interference versus diffraction, and then we will also discuss different types of diffraction and then come to diffraction due to single slit. And in diffraction due to single slit, we are going to discuss the conditions for principal maxima and also the conditions for secondary maxima, and also see the intensity distribution curve, how the intensity is going to be distributed in a diffraction pattern. Now coming to diffraction, a wave passing through a small opening will diffract as shown. Now if you see, this is a wave that is incident on a surface, and this is a surface which has got a small opening. I may say that the small opening is AB. So when the wave is incident, what is happening? It diffracts. It is means if you imagine light has to come, and if you keep a screen here, you will only see the shadow of the light here. This means after the opening there are waves traveling in directions other than the direction of the original wave. So even in this direction and this direction we are having the rays. This is because of diffraction. And diffraction is why we hear the sound even though it is not in a straight line from the source. This is what we observe in our day-to-day life. Sound waves will diffract around doors, corners, and also if there are some other barriers. And the amount of diffraction depends upon the wavelength. That is why we can hear sound around the corners but we cannot see them. Now let us see the diffraction pattern. To investigate the diffraction of light, we consider what happens when light passes through a very narrow slit. So we have seen this is the slit, this is the slit. W is representing the width of the slit. Now when light is incident on this, so you are having the light traveling straight, and also in other directions other than the direction of the light that is incident, you have the light rays. And because of this, you are seeing a pattern like this on the screen. So what you have is a central bright fringe, then this is a dark fringe, bright, dark, bright. So here also this is dark, bright, and so on. So this is the type of pattern you see in case of single slit. So we are calling it as diffraction pattern. Now if light is a wave, it will diffract around the slit. If light is a particle, so what happens? You will see only one spot on the screen. But because we are considering light as a wave, it bends around the corners of the obstacle. So if you see, this is the obstacle. If light is coming and falling on this, it bends around the corners of the obstacle and you get a shadow here. Means it is coming into the geometrical shadow of on the screen. So there is a bright spot on the screen. Now in our day-to-day life, what we see, when a narrow opaque obstacle, opaque means through which light cannot pass, is placed in between the source and the light and the screen, light bends around the corners of the aperture. Aperture means it's a very small opening. And this encroachment of light we are calling as diffraction. And for diffraction, the size of the aperture should be very small. Very small means comparable to the wavelength of light. So the size of the aperture, if it is very small compared to the wavelength of the light that we are using, you will be able to see the diffraction phenomena. So in our day-to-day life, what are the things we see here is when light bends around the edges. Okay, so here we see a blade where the edges are very thin. So when light falls on it, what happens? The edges are not sharp, but the intensity is distributed in a certain way, depending upon the nature of the aperture. Here you see, if you go to a place where you see the light that comes through a very narrow opening. Okay, and when light travels through this narrow opening or an aperture, it bends, and because of which it spreads. So these are few examples of diffraction. So let us now define exactly what is diffraction. Light bends around the corners of the obstacle and enters into the geometrical shadow. That is the diffraction phenomena. So what we have observed now is light that is coming and traveling through the narrow slit. So when it comes here, it enters this geometrical shadow. So the size of the obstacle should be comparable with the wavelength of light, and then you will see bright and dark fringes that form a diffraction pattern due to the mutual interference of the secondary wavelets originating from the wavefront. So this is what we will understand now. What are these secondary wavelets and how they are interfering with each other to give the diffraction pattern. Now let us understand the difference between interference and diffraction. So in interference, what we have seen, light from a single source is allowed to pass through two narrow slits, S1 and S2. So this light, even if it is not a monochromatic or a coherent source, after passing through these two, because they are placed equidistant, they will become coherent. So these are the two coherent sources that are sending out waves like this. Now, if these waves superimpose on each other and a crest falls on a crest, you have a bright band, and a crest falls on a trough, you have a dark band. So you can see this is the bright band, this is the dark band, again a bright band, dark band, bright band, and so on. So how are we getting the regions where they come in phase? We have a bright band, and where they come out of phase, we have a dark band. So here what we are seeing, there are two sources. They are sending out waves. The waves coming from these two sources will interfere with each other and you get an interference pattern. And in interference pattern we have seen, no, there will be, in case of Newton's rings, what we have seen is alternate dark and bright rings formed. Now in diffraction, what we are going to see is, this is the wavefront, that is incident, and this is the obstacle, okay, or the object edge. This is a narrow aperture, we can say. Now each point on this will act as a secondary source according to Huygens principle we have seen. So each point will act as a secondary source and sends wavelets, and these will now interfere with each other and you get the diffraction pattern. So if you see on the screen, so it enters the geometrical shadow, you have a bright, dark, fringes, so on. And if you see in the light, this is the pattern how you see. Now let us compare and contrast. Superposition here is due to two separate wavefronts originating from two coherent sources. So in interference, what we have seen, two separate wavefronts coming from two coherent sources. And in diffraction, superposition is due to the secondary wavelets originating from different parts of the same wavefront. We are having a single wavefront, but from different parts of the wavefront, whatever secondary waves are emitting, they are interfering with each other. And the fringes normally have equal width. So we have already derived expressions for the fringe width in interference. we have seen that the fringe width is same for bright bands and dark bands. But here the width between the fringes is never equal. So even in the diagram we have seen, see here the width of the dark fringe is less but the bright fringe is more, this is less. And as you go away also the width keeps on and the intensity also keeps on decreasing. All bright fringes have the same intensity. If you are talking about bright fringe, all bright fringes have the same intensity. All dark fringes have the same intensity. But here the intensity of the bright fringes decreases with increase of order. Means as you go away from the center, n is equal to 1, 2, 3 and so on. So what happens? The intensity keeps on decreasing. And the dark fringes have zero intensity. Means dark means here it is completely dark. They cancel each other and they have zero intensity. But here the intensity of the dark fringes is not zero. Now coming to the types of diffraction, we have two types of diffraction. One is Fresnel diffraction and the other is Fraunhofer. Fresnel is the name of the scientist. He explained the diffraction pattern with the help of a phenomena which we call it as Fresnel diffraction. And then we also have another scientist by name Fraunhofer. He explained with a different setup which we call it as Fraunhofer diffraction. So first let us see Fresnel's diffraction. In Fresnel diffraction, the source of light or the screen are usually at finite distance from the diffracting aperture. So suppose if you take this is the aperture, this will be the source. So the distance between the two is finite. That is very important. In Fresnel, if the source is at a finite distance from the aperture, you call it as Fresnel diffraction. And no lenses are used here to make the light to be incident or to capture the image. And the incident wavefront is either spherical or cylindrical. If you see, the waves that are coming are spherical or cylindrical. In Fraunhofer diffraction now, the source of light and screen are at infinite distance from the diffracting aperture. So if this is the aperture, this is the aperture, the source is at infinity and the screen is also at infinity. Both are at infinity. Means if you have a source from where the light is coming and it is at an infinite distance and the light passes through the aperture, then what we do is we will have to capture it by placing the lenses. So we are going to use lenses. So this is achieved by placing the source and screen in the focal plane of the two lenses and the incident wavefront is plane. So whatever wavefront we are talking about here is a plane wavefront. So the same thing we have discussed. So in compare and contrast, so a point source illuminated with a narrow slit is used. Here we are using an extended source at infinite distance. The wavefront is either spherical or cylindrical. Here the wavefront is plane. The source and screen are at finite distance from the obstacle or the aperture. Source and screen are at infinite distance. No lenses are used to focus the rays. So a converging lens is used to focus the parallel rays. Because when we have the source at infinity, the rays that are coming from infinite distance are parallel. So to focus them, we use a converging lens. Now let us see the diffraction due to single slit. How diffraction occurs when we have a single slit, one single slit. So let a parallel beam of monochromatic light of wavelength lambda be incident normally upon a narrow slit of width AB is equal to E. So this is the slit, a narrow slit which we are representing by AB, and the width of the slit is E, small e, very small, it is E. Now this is the source of light which is a monochromatic source. So light from the source is allowed to pass through the aperture. So when it passes, generally around the corners it will bend. There is bending around the corners of the obstacle. And the diffracted light is focused with the help of a convex lens. So we are keeping a convex lens because we need to focus and capture it on a screen. So we are using a convex lens on a screen XY. We will name the screen as XY. The diffraction pattern obtained on the screen consists of a central bright band. See, if you see these two rays, they are traveling the same distance. So there is no path difference, no phase difference. So they arrive in phase. So this will be a bright band. So what you have here is a bright band, central bright band, having alternate dark and weak bright bands of decreasing intensity on both the sides. So once you have a bright band, there will be a dark, bright, and so on. But the intensity of these bright and dark bands keeps on decreasing as you go away from the center. Now let us see the notation. The width of the slit AB, we are denoting it by small e. We are considering a plane wavefront. This is a plane wavefront. We are denoting by WW prime. And the wavelength of the monochromatic light we are using is lambda. And we are using a convex lens to focus the diffracted light through the slit onto the screen. And the central maximum is P0. If you see here, P0 represents the central maximum. Then the secondary wavelets in the slit AB make an angle theta with OP0 and are brought to a point P1 on the screen. So those rays which are traveling straight, they arrive at a point P0 on the screen. This gives rise to central maxima. But those that make an angle theta, they are bending, this also bending at an angle theta. So all of them are brought to a point P1 on the screen. So they are making an angle theta with OP0. So those which are bending, they are coming at P1. Now in terms of wave theory, if we understand, the plane wavefront is incident on the slit AB. And according to Huygens principle, each point in AB, that is the slit, sends out secondary wavelets. This is what we have understood in diffraction. We have a single wavefront. This wavefront, when it is incident on the aperture, each point will act as a secondary source and sends out secondary wavelets. And the rays proceeding in the same direction as the incident ray are focused at O. If they are traveling in the same direction without bending, they are focused at a point O, that is the center of the screen. Now, since they have traveled the same optical distance, there is no path difference. So, when there is no path difference, they will interfere constructively. And whenever there is constructive interference, the point O is bright with maximum intensity. So, this is what we understand in diffraction. Now, let us see, draw AK perpendicular to BK. So, we are going to drop a perpendicular AK to BK, and as the optical paths from the plane AK to P are equal, the path difference between the wavelets from A to B in the direction theta will be BK. That is equal to AB sin theta. We will understand with the help of the diagram. And AB is the width of the slit, which we have denoted it by small e, sin theta. Now the corresponding phase difference will be 2 pi by lambda into E sin theta. So we have already seen for a path difference lambda, there will be a phase difference of 2 pi. Now here we are seeing that the path difference is E sin theta, that is AB sin theta. So for E sin theta path difference, what will be the phase difference? So this will be 2 pi by lambda into E sin theta. So this is the phase difference. Now the width AB is divided into n equal parts because we have seen each point will act as a secondary source. So the width of the slit, we are dividing it into n equal parts, and the amplitude of vibration at P due to the waves from each slit is A. So A represents the amplitude of vibration. Now we'll see here what we have tried to understand here is from A, we have dropped a perpendicular onto this. This is angle theta. So when we want sine theta will be equal to BK upon hypotenuse AB. So BK is equal to AB sine theta. AB is nothing but the width of the slit, that is E sine theta. So we have written E sine theta. Here we are writing it as BC. It's okay. So instead of K, we are talking it as BC. Now what is the phase difference? 2 pi by lambda into E sine theta. Now we are dividing this into n equal parts. We are dividing the slit into n. Each point will act as a secondary source. And the path difference between any two consecutive ways. We have seen the path difference between the ray coming from A and the ray coming from B. That is 2 pi by lambda into E sine theta. Now we have split it into n parts. So the path difference between two successive, this one and this one, will be 1 by n into 2 pi by lambda into E sine theta. This is for A and B. Since we have split it into n parts, so the phase difference will be 1 by n into 2 pi by lambda E sine theta, which we will denote it by D. Now what we need to understand here is, if there are n number of vibrations of the same period and the same phase difference acting on a same particle, the resultant can be obtained by constructing a polygon of amplitudes. Here we need to understand the polygon law of vectors. We'll go back to the basic, that is polygon law of vectors. When you have a number of vectors, okay, if you have to find the resultant of all the vectors. Now what we are having a number of rays coming from different points on the same wavefront and arriving at a point. So what will be the resultant amplitude at that point? So if this is one vector, second vector, 3, and so on, there may be, polygon means many, there may be many. If you can construct a polygon like this, the closing side taken in the reverse order will give us the resultant R. So the closing side gives the resultant amplitude R, and angle gives the phase of the resultant vibration. So this is what we are going to apply now for the diffraction pattern. Now what is the resultant amplitude given by? R is equal to A sine nd by 2 by sine d by 2. This is the formula for the resultant. A represents the amplitude, and what we have denoted by D is nothing but 1 by n into 2 pi by lambda E sine theta. This we have named it as small d. So sine A sine nd by 2 upon sine d by 2. So let us substitute for d by 2. So when we write sine, A is there, sine n into d by 2. What is d? 1 by n, 2 pi by lambda E sine theta by 2. So 2 and 2 will get cancelled, n and n will get cancelled. So what we are left with is A sine pi E sine theta by lambda in the numerator, and in the denominator we simply have sine d by 2. So what is sine d by 2? Sine 1 by n into 2 pi by lambda into E sine theta by 2. So 2 and 2 will get cancelled. So in the denominator we have sine pi E sine theta by n lambda. So we have sine pi E sine theta by n lambda. And now we are going to substitute pi E sine theta by lambda is equal to alpha. So we are doing this substitution. Pi E sine theta by lambda is equal to alpha. So in the numerator what we have? A sine alpha by sine alpha upon n, because in the denominator we have n here. So sine alpha by n. So the resultant amplitude is given by A sine alpha upon sine alpha by n. We know that the width of the slit is very small, and we are dividing it into n small slits. So what happens? The value of alpha by n is very small. Alpha is small, alpha by n will be very small. So whenever we have small angles, sine alpha should be equal to alpha. So here sine alpha by n will be equal to alpha by n, whatever the angle we are taking. So we are going to substitute this. So a sine alpha by n, since alpha by n is very small. So if we substitute and take it up, we write it as Na upon sine alpha by alpha. Na is what? A is the amplitude of each wave, n for n number of waves. So let us substitute for capital A is equal to Na, the resultant amplitude. So I can write capital R is equal to A sine alpha by alpha. So once you get the resultant, we have to find the intensity. Intensity is nothing but it is proportional to the square of the amplitude. So R square. Our R is A sine alpha by alpha. So A square will be A into sine alpha by alpha whole square. So what we are going to write here is I is equal to A sine alpha by alpha whole square. So that will be A square sine alpha by alpha whole square. So this is the formula for intensity we are getting. Now to write the resultant amplitude, so we are now writing R is equal to A sine alpha by alpha. We are going to expand this sine alpha term here. We know the expansion for sine x is equal to x minus x cube by 3 factorial plus x power 5 by 5 factorial minus x power 7 by 7 factorial and so on. So we know this expansion. Now for sine alpha, if I write in place of x, I write alpha. So sine alpha will be equal to alpha minus alpha cube by 3 factorial plus alpha power 5 by 5 factorial minus alpha power 7 by 7 factorial and so on. Now if I substitute here for sine alpha, we have R is equal to A by alpha into alpha minus alpha cube by 3 alpha 7 by 7 factorial and so on. So this is what we have written here. Now in all the terms, you have a numerator. In the numerator, alpha is common. We can take out one alpha common. So R is equal to A by alpha into alpha. So this will become 1 minus alpha square by 3 factorial plus alpha power 4 by 5 factorial minus alpha power 6 by 7 factorial and so on. So this is what we are going to get, because alpha and alpha is going to get cancelled. So what is the resultant now? R is equal to A into 1 minus alpha square by 3 factorial plus alpha power 4 by 5 factorial minus alpha power 6 by 7 factorial. Now we are going to see the principal maxima. That means when the points arrive at a point on the screen at the center, I will be maximum when R is maximum, because I is equal to R square we have seen. So when the resultant amplitude is maximum, the intensity also will be maximum. So when the intensity is maximum, you get the principal maximum. Now for maximum value of R, because we have seen that R has to be minimum. So if R has to be minimum, then what happens? The negative terms must vanish. So all these terms, whatever we have, all the negative terms should vanish. Then what you have? You will only have R is equal to A into 1. So this gives us A. R is equal to A. All the other terms are vanished. So R is equal to A. So I max will be equal to R square, that is A square. Now we know that alpha is equal to, we have done the substitution, alpha is equal to pi e sine theta by alpha. This should be equal to 0, or sine theta should be equal to 0. So when will sine theta be equal to 0? When theta is equal to 0. So we are able to understand the substitution. Alpha is equal to pi e sine theta by lambda. Pi is a constant. E is the width of the slit, which cannot be equal to 0. Lambda is the wavelength of light which cannot be 0. So what can be 0 here is sin theta. For alpha to be equal to 0, sin theta has to be 0. So for sin theta to be 0, the value of theta should be 0. There can be other values also, 2 pi, 4 pi and so on. But here we are discussing about the principal maxima. Principal maxima means when the light rays are coming straight and when the angle through which they are bending is 0 or there is no bending, theta is equal to 0, we'll have a maximum. Means the condition theta is equal to 0 means that the maximum intensity is formed at P0 and we call it as the principal maxima. So whenever the rays are coming straight without bending and they arrive at a point on the screen, we have a maxima. The intensity is maxima and we call it as a principal maxima. Now condition for minimum intensity. So when do we have minimum intensity? I will be minimum when sin alpha is equal to 0. So when will sin alpha be equal to 0? For all values of alpha taking plus or minus pi, 2 pi, 3 pi, 4 pi and so on. For all these values we can have sin alpha is equal to 0. Now we will write the conditions for minimum intensity we are seeing. We will not consider m is equal to 0 because for m is equal to 0 we are getting a maxima, principal maxima. Okay, so let us only take the values for m is equal to 1, 2, 3 and so on. For m pi, we will be considering only 1, 2, 3 and so on. So we will obtain the minimum intensity on either side of the principal maxima for all these values. Now the condition for secondary maxima. So what is the condition for secondary maxima? Now if we see the diffraction pattern, at the center, we are having a principal maxima. Then there is a minima on either side. So if this is the principal maxima, this is the minima. On either side, in between the maxima, this is one minima and one minima. Between these two minima, you will have a secondary maxima. So in between the minima, there exists a secondary maxima and their position can be obtained by differentiating the expression for I. What is the expression for I? We have taken I is equal to R square and the value of R we have taken as A sin alpha by alpha. So when we have taken the square, it is A square sin alpha by alpha whole square. This is the formula for intensity. Now when we want secondary maxima, we need to differentiate it with respect to alpha. So we take di upon d alpha or d by d alpha of A. This is the formula for I. So now we are going to differentiate. A square is a constant, so we will keep it outside and we'll use the formula d by d alpha of u by v. U by v method we use. So substituting what we get 2 sin alpha by alpha into alpha sin alpha minus sin alpha by alpha square is equal to 0 after differentiation. Now two conditions. If this whole thing has to be 0, either our sin alpha has to be 0 or alpha cos alpha minus sin alpha has to be 0. Okay, but sin alpha is equal to 0 gives the position of minima. This we have discussed previously. So we cannot consider sin alpha is equal to 0 because that is giving us minima. So what is the next thing we have to consider? Alpha cos alpha minus sin alpha has to be 0. So we have taken alpha cos alpha minus sin alpha is equal to 0, or we rearrange the terms to get alpha should be equal to tan alpha. So we have alpha is equal, if we write here alpha, it will be sin alpha upon cos alpha. So sin upon cos will be equal to tan. So what we are getting here is alpha is equal to tan alpha. Now we are going to plot the graphs to understand the secondary maxima where they are formed. So we'll plot the graphs for y is equal to alpha and y is equal to tan alpha. Now the graph y is equal to alpha is a straight line graph. Y is equal to mx plus c. It is a straight line graph. So what we get here is a straight line. This represents y is equal to alpha. Now the graph for y is equal to tan alpha, we are getting the curves like this for different values. These are the curves for tan alpha. Now let us see the point of intersection of these. So the point of intersections are alpha is equal to 0, 3 pi by 2, 5 pi by 2 plus or minus, and so on. These are the points of intersection. Now when we substitute these values in equation 1, that is I is equal to a sin alpha by alpha whole square. So what we get for alpha is equal to 0, I naught is equal to a square, that is the principal maxima. So we know the condition for principal maxima, and we know that when sin alpha is equal to 0, we have the minima. Now where is the secondary maxima? So for alpha is equal to 3 pi by 2, from the graph we have seen the point of intersections. Alpha is 3 pi by 2. Then I naught will be a square sine alpha by alpha whole square. So in place of alpha we are putting 3 pi by 2. So sine 3 pi by 2 by 3 pi by 2 whole square. So that gives us a square by 22. This is the first secondary maxima. This is the first secondary maxima. And now the next one is alpha is equal to 5 pi by 2. So we are again substituting alpha in a square sine alpha by alpha whole square. So in place of alpha, what we are going to put 5 pi by 2. So sine 5 pi by 2 by 5 pi by 2 whole square. So we have a square, and when we simplify it, we get a square by 62. So this is the second secondary maxima. First secondary maxima and the second secondary maxima. Now let us understand the pattern. What we have seen here at the center, where the rays do not bend, okay, we are having a principal maxima whose intensity is maximum, given by I is equal to a square. And then we have minima. Where are the minima? At pi, 2 pi, 3 pi, minus pi, minus 2 pi, minus 3 pi. All these are giving us minima. So these are the positions of minima. So at 0, we have the principal maxima. At points plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, we are having minima. And in between two minima, we have secondary maxima. So these are secondary maxima. So what are the positions of secondary maxima? 3 pi by 2, 5 pi by 2. This is 3 pi by 2. This is 5 pi by 2. And on the other side also, minus 3 pi by 2, minus 5 pi by 2, and so on, minus 7 pi by 2, and so on, we have the secondary maxima. So when we look at a diffraction pattern, what we have is a principal maxima, and for all values of pi, minus pi, 2 pi, 3 pi, minus 2 pi, minus 3 pi, we have the minima. And for values of 3 pi by 2, 5 pi by 2, minus 3 pi by 2 and minus 5 pi by 2, we have secondary maxima. So whenever we see a single slit, this is the type of pattern we get, where we have a principal maxima followed by minima and secondary maxima. Now if we see the intensity distribution, how the intensity varies. So naturally for the principal maxima, we have sine square alpha by alpha square. Actually it should be a square sine square alpha by alpha square. This is the principal maxima. And then here the intensity is 0. So the diffraction consists of a central bright maxima with secondary maxima and minima on both the sides. So on both the sides, means for plus pi, 2 pi, 3 pi, minus 2 pi, minus 3 pi, we are having the minima, and in between for 3 pi by 2, 5 pi by 2 and so on, we are having the secondary maxima. Means here also the energy is getting distributed and the conservation of energy is followed. Wherever there is maximum, it is taken from minimum. So thank you, and see you again in the next lecture.
Like, share and subscribe. Hit the bell icon for more updates.